between the lower and higher frequency of the carrier, then for this particular procedure, we need to pick the 1 megahertz, like 1000 kilohertz carrier frequency, right? So how we can do it? We again connect this wire, yellow wire, as we see, right, from the function generator. Sorry, not the function generator. It's the AM generator output to this guy, frequency counter, and then the display will tell you when you have to change the RF tuning knob to find it. Whenever it displays 1000 kilohertz, then you stop, right, changing the RF tuning. Now you got your 1 meg carrier, right? So you set your 1 meg carrier with this machine, right? Now describe the effect. Okay, so next what you have to do, vary the carrier level control, and then RF gain control between minimum maximum. Describe the effect the control have on the waveform displayed on the oscilloscope. So now you fix to 1 megahertz frequency. Now the next part that you do, so now you know how the frequency is changing, right? Using the RF tuning knob, you can change the frequency. This guy, you can change the frequency. Now you also need to see what are the effects of this knob and this knob. What do they do, right? This carrier level and the gain. So you put both of them like separately, this maximum and minimum, and observe what it shows. Then again, you do this one, maximum and minimum, and observe what does it do. What does it do, right? So as you see, this is gain. So gain means you are amplifying or attenuating, depending on whether the gain is over 1 or lower than 1, right? So that is the purpose of the gain. So in fact, that means when the gain is maximum, you get an amplified form of the signal. So amplified means you now have a higher amplitude signal, right? Because it doesn't do with the frequency. Frequency is fixed to 1000 kilohertz. Now the gain will amplify the signal, output signal, so you get a higher amplitude signal. The carrier level, as the name indicates, carrier meaning it is controlling the carrier, and level means the amount of carrier you're sending, right? So if the carrier level is high, again, it will give you a high amplitude signal. If the carrier level is low, it will give the low amplitude signal, right? Okay, so the gain and carrier level seems working similar thing, right? Once we fix our RF tuning to 1000 kilohertz, then the gain and RF tuning doing the same, right? Okay, so far so good. Okay, now we know how to control the frequency of the carrier by tuning the RF tuning, by fiddling or playing with the RF tuning. Now we also see how you can change the amplitude, either by changing the gain or changing the carrier level, right? Now the next step is to make a carrier frequency of 2 kilohertz, right? Let me see. No, this is not from the carrier. So now we are gonna go to the dual function generator. So our introduction with the carrier, I mean the what you may call the amplitude generator, right? AM generator is done. Now we're gonna work with the function generator, dual function generator. Let's see what it has. So we are kind of familiar with this line, right? So this is the input as the message. This is the carrier level. This is the gain. This is how you control the frequency of the carrier, and the output will come out from here. So this is basically this machine works this way. Now, the second equipment that we need to work with is called the dual function generator. So we have 2 channels. That means we can create 2 signals, 2 sine waves. So this is one channel, right along the horizontal line. This is one channel. Right around this is the second channel, right? Now let us see what we have to do with this. connect output A of the dual function generator to the oscilloscope. Now, if you could read, this is called output A and this is called output B. So we're going to connect this one to another oscilloscope, right? So here, let's connect this guy with the oscilloscope and just to see. So here, we connect this guy with the oscilloscope and we need to see, or we need to create a sine wave with 2 kilohertz signal, peak to peak amplitude of 400 millivolts, right? Okay, so let's see quickly here what's going on. If I can amplify again, let's see. Sometime, okay, so this is, as you see, output A. Now, how to control the amplitude and frequency of this channel. Now here, on this part, you see the frequency, and on this part, you see the output level, right? So just like carrier level, we increase the amplitude of the carrier. Output level will increase the output amplitude, right? Whatever the output, A or B. And this guy controls the frequency of that output. So this knob A under A will control the frequency of A. This knob under A will control the amplitude of A. So now, these are the two things that we need to control to pick a particular sine wave. And here, as this is a function generator, it also has different other functions like square wave, rectangular wave, and etc. But we need to pick the sine wave. So if you press this button, then the output will come as sine wave. Now you change the frequency by using this knob, and you change the amplitude by using this knob, right? So what we need is a 2 kilohertz frequency and peak to peak 400 millivolts. Now, I may ask a question here. Now, there are some buttons here. So I'm just going to ask if anyone has any guess. Lopez, do you have any guess of this button? Attenuation dB.
Um, I would say just to reduce the amplitude of any like other signals, like noise.
Uh, okay, so we have an, this is just a pure, what we call voltage source, right? So
Mm-hmm.
it should not have any noise. We are not putting any noise here. Yeah, so it seems like we are doing some attenuation, but this is not for, let's say, removing some bad signals from it. We are not using this. Okay, so at least you have some good guess. Okay, good. Now here, particularly, now as our range of amplitude is varying from, let's say, 5 voltage to even 1 millivoltage, right? So the range is very, very big. Now, when you do not use this at all, right, that means you are not attenuating, then the lowest amplitude you might get is sometimes big enough or more than enough that you require. So here our amplitude has to be very low. 400 millivolt means zero point 0.4 voltage. It's very low voltage. Now sometimes just directly getting the output is not gonna give you that low voltage. So what you could do, you can use this attenuation button to reduce the voltage level or the amplitude even further. So if you cannot get 400 millivoltage just by the normal output, even though you put the output level, this one to lowest, yet the signal is more than 400 millivoltage. Let's say it's more than 1 voltage. Then you have to use this button to reduce it even further. So that's why this button are there. And in fact, in actual lab, it doesn't appear less than 1 voltage when you have this knob goes to minimum, yet the amplitude, the lowest amplitude you can get is more than 1 voltage. So you have to use one of these knobs. Mostly you have to use the second one. As you see, the first one is called 0 dB, meaning no attenuation. Then the second one is 20 dB. So this is a significant attenuation. And if you need to know further attenuation, you can use 40 dB attenuation, right? So in fact, for this case, you have to press this one, the 20 dB. As you see, it's already pressed. Probably once it is pressed, then it was the picture was taken anyway, right? So we have to press this one to make it 400 millivolt amplitude. Uh, so now we set our what may call the carrier to 1000 kilohertz. We set our message to 2 kilohertz and 400 millivolts, peak to peak, right? This amplitude. Inject the 2 kilohertz message signal to the audio input of the generator, AM generator. Turn the carrier level and the RF control to max. Set the oscilloscope to observe several periods of this. Sketch the resulting output. It should resemble the one that shown at the left. Something shown at the left or somewhere. Oh, right here. Okay. And you already got this one, right, from your pre-lab. So we know what output we are going to get. We already see, but let us see the connection. So we have to put this guy to audio input of the AM generator. So let's see audio input. Now we test by the oscilloscope and pick the right frequency that we require for this case and amplitude. Now
Professor?
yes, do you hear me?
Yeah, we hear you now. There was we lost connection, I guess.
Yeah, it's
Okay.
happening like that.
Yeah, sorry that as I told you before, that's why I put all my audio and video out of this thing. Sometimes because of the heavy load, it disconnect or could not carry the burden. So yeah, so just bear with me. Whenever you have disconnection, it will come quickly.
Professor,
Disconnected. Yes,
sorry.
go ahead.
Can you hold the class in Zoom?
Uh, the thing for this one is we have many things here on the blackboard. I use many things together, right? So
Oh,
not only the like the lecture, I have all the other parts are there as well, right? So that's why I love using blackboard. But even if we use Zoom, sometimes Zoom also cause trouble. Like I heard a couple of days before, it was down for 2-3 hours, right? The Zoom. But in this case, maybe a little bit of disconnection, maybe a couple of minutes or less, it should be okay, right? And we're not gonna disconnect like for a long period of time. That's for sure.
oh,
Yeah. So okay. Yeah. Whenever it's disconnect, it will reconnect. Maybe in 1 minute or so. Okay. So what I did here, if you can see my screen again, right? So we create our message signal as 2 kilohertz and 400 millivoltage. And now we connect it to the input of this guy. So before it has only carrier frequency. Now we input there, right? So it says connect to okay. So you got it again?
Yeah, we can hear you and see the screen again.
Okay, good. Okay. Okay. So here now we put our message there, right? The message is there. So now our thing is kind of done. So we create the message of 2 kilohertz and 4 millivoltage, 400 millivoltage, and then we connect to the input. The name of the input is called audio input, right? Then it will start to give you modulation, right? Now on the oscilloscope, you're gonna start to see modulation. It was only one sine wave before because there was no message. Now we put the message, modulation will be done or will be going on, and then you see a signal similar to this one that you saw in your pre-lab, right? This one, right? So what we have to do now, let's see. If you have difficulty with synchronization, like this is part of the how to run the oscilloscope. What happened is sometimes it was not stable because of high frequency, low frequency combination. So sometimes you have to play with the trigger mode of the oscilloscope to make it stable. But as we are not using it, so we don't worry about that much at this moment. Now let's see what happened to vary the RF gain control. Is the effect similar to the obtained in 4? That means if you change the gain, right, for this case, here you change the gain of this, sorry, where is the gain? This one is the gain, right? Okay, let me go back there again. So the if you change the gain, this guy, then last time we see its amplitude is increasing or decreasing, right? Now, what you're gonna see is as this is the gain, so you combine carrier and the message, then combination is done where? Right here, as you see, this is where the mixing is done, right? So mixing is done here. Afterward, this is the combination of message and carrier. Now it is increasing. Probably you see this gain, I don't know, in the pre-lab, maybe you use it or not, but this gain will increase the whole thing, right? So in fact, you're gonna see the similar thing. So it is actually the amplitude is increasing, right? Now vary the carrier level control between minimum max and describe what happens. Now here it will be an interesting thing you're gonna see if you change the carrier. So when you change the gain, it is actually acting on the combination, right? Combination is here, so whole thing will be like increase or decrease by amplitude. But here, this carrier level is only for the carrier, right? Not for the message itself. So whenever you change the carrier level, only the carrier amplitude will decrease or increase. The message stays the same, right? So in that case, what could happen? Your carrier level is fixed, your message level is fixed, but the carrier amplitude is changing, right? Let me see. Anthony, what do you think may happen?
You're talking in regards to the carrier
Carrier
level.
level,
What happens?
right? Carrier level. Yeah. If you change the carrier level, what will
It'll
happen?
only affect the amplitude of the carrier signal, not the input signal. Correct? Or
Exactly.
okay.
That's exactly. But like what we need to know is what will happen to the observation. What do you see? So what you see in general is this, right? As we know, we see in general this thing, right? Now, if you lower or increase your carrier level only, not the message, what do you think will happen here?
Well, since the message signal is the one that's controlling the amplitude of the carrier, and if you lower
Uh-huh.
the level of the carrier, I think it'll affect the output by action on. I don't think
Let's
it'll
see.
decrease the carrier level, so that shaded uh area will decrease. It won't be at the envelope. Is that correct?
Right, the envelope is not changing. Like the boundary of the envelope is not changing because this is following the message, right?
Yeah.
Amplitude of the message. But as the carrier is just whatever is inside the envelope, that is the carrier level. So if you decrease the carrier level, right, then these two peak, right, will getting close to each other, right?
Yes.
At at some point, this lower part will like cross each other, right? Because the carrier is reducing, right?
Yes.
So then, uh, if it is reducing, then sometimes it may go cross each other. So this envelope may cross this envelope, right? So in that case, this is called uh, over over modulated index, or sometimes if it is go the other way, it's called under modulated. So what happen is if the modulation is under over, then it's hard to detect the envelope edge because now they are crossing over, right? One gets into the other, right? I don't know whether we have any figure. Let me try to find. I think what you're gonna see is instead of, let's say, I'm gonna try to make something similar to this. Hold on, let me see. Quickly, it's gonna be here. Let's see this. Okay, so now, right now, this is what is going on, and let me do it quickly if I can. Mm. So this is what happened at this moment, right? You have the thing in between, right? Now, if your carrier is lower the frequency, then it will go like this, right? So you're gonna see something like this. Now here, this part is very difficult to recognize because the envelope is looking like this now, right? It's not anymore a sine wave, right? Do you see that? So this is what's gonna happen when you vary only the carrier, right? So whenever you need to, where am I? Oh, here. So whenever from the observation, right, you need to check whether it's going like over modulated or not, or under modulated or not. This is always the better signal, right? So then you can follow the envelope nicely that follows the amplitude of the or the message, right? But if they are overshooted like this, then the envelope is not following a sine wave. That is trouble, and that is called over modulated or under modulated. So if you change the carrier level, that will happen, right? For this case. Okay, and waveform are a result of, as you see, overmodulation, which occurs when the amplitude of the message signal becomes larger than the carrier wave amplitude, as you see here, right? So this is going to happen. Return both controls to maximum position and vary the frequency of the sine wave between 1 to 10. What changes? Now, vary the frequency of the sine wave between. Okay, so here we are changing the message. So if you change the message, what is gonna? Oops, I should do it like this. Hold on. So then we can use this figure to quickly see what's going on. So here, this is our thing, right? So everything is in between here, right? Now, if we change the frequency of the sine wave message, then the envelope will increase its frequency, right? The whole envelope frequency will increase. So whenever you have for 1 kilohertz, the envelope frequency is like less. And let me do it. Okay, so let us do this so that we can see at least what's going on. Scooping. Okay, so let's say when the frequency is this, then you see this. And when you increase the frequency, then you probably see this, right? Right, so you're gonna see like this, right, when the frequency is increased by the message signal, from the frequency of the message signal is increased. Then readjust the frequency of the sine waves to 2 kilohertz and set the RF control to 1/4. So this is just setting. So again, we fiddle or play with the message signal and see from 1 kilohertz to 10 kilohertz. What does it look? It looks something like this, right? So maybe let's do this. We can at least have a sense like what's going on, right? And try to imagine the thing is in between, right? Here you have all the oscillation, right? And here you have all the oscillation. Okay. Now you come back to the same frequency that we said at the beginning, 2 kilohertz. Disconnect the frequency counter and connect output of the AM generator to this input of the receiver. So now we are connecting the generated output to the receiver, right? So here we generate this output. Now instead of sending to the counter, right, we are sending this one to the receiver, right? So from here we're sending to receiver. Let's see, where is receiver? This one, right? Let's see, make it a little bigger and able to see what is whether receiver or not. Yeah, this is the receiver, right? So you connect it to the receiver side. Let me see. It says probably RF 50 ohm, 50 ohm input, right? So this is correctly said, connected. So this is the 50 ohm input that we connect, and then let's see what happens. So it says cable to connect. Disconnect the frequency counter, connect to the output of the AM generator to 50 ohm RF input to the receiver. So this is 50 ohm RF input to the receiver side, right? Now we are seeing what is there in the receiver side, right? So we're gonna see that thing now. So here, use the BNC cable connector, audio input, output of the receiver to one of the audio inputs of the dual audio amplifier. Okay, so now what we are doing, so we connect this input. So whatever coming here is the amplitude modulation. And it comes to the receiver side. And then after the receiver is done, receiver side, then we're gonna connect the output of the receiver. Let's see which output of the receiver. Audio output of the receiver. So there is an output called audio output. Let's see, this is RF output, mixer output. This is F output. Okay, I think it's hard to see which one is the audio output.
I think it's the last one, number 8, because it kind of says audio there. I can see the DIO.
Okay, good. You have a very good eyesight. Yeah, it looks like this one is the guy. Okay, so here, this is our output of the receiver, and then we're gonna connect it to our last guy. Last guy is this audio amplifier. We're gonna discuss what it does. It does simply, it works like a speaker, right? So it's nothing but a speaker with an amplifier. So let me, okay, so I'm gonna do all this connection right here. Okay, so now we come here, all the way here. Let's see how much first we can make yellow. Okay, so now let us make it smaller. Okay, good. Now we connect this guy with the audio amplifier. right here. Yeah, the channel maybe a little bit smaller, 150, just to see them together. Good. So now from the output, we connect it to the audio amplifier. That's what the procedure says, and we did it, right? Plug in the headphones. Okay, so now what we have to do, we have to listen. Listen to this guy. So as you see, it has a speaker. Either you can use the speaker without a headphone, or you can use the headphone just to use headphone speaker, right? So whatever you do, you listen something, right, from this output. Now here there is a switch. The switch is if you press on, then this will connect to the speaker, and if you use the headphone, you can use the headphone. So the bottom line is, after you connect this, this will give you the audio signal to the speaker, or it will send this signal to the speaker to hear the audio part of it, right? Or one part that we can see this one by oscilloscope, right? We can see the time domain pattern, but also we need to hear what it feels like, right? So we send this one here and to hear what it is, right? What kind of sound or volume you getting. So this is what is done for this step. Connect the frequency counter to the oscilloscope output on the AM's receiver. Okay, the frequency counter to the oscilloscope, local oscillator output of the AM receiver. Depressing detector switch on the module and turn the AGI one position. Turn the receiver RS tuning control until the frequency counter reads 1455 kilohertz. You should now be tuned to the broadcast and hear the 2 kilohertz tone. Fine tune the receiver until the signal is loudest and record the local oscillator frequency. Note that local oscillator may change slightly, but it should be in range within this. Okay. The local oscillator is designed to provide an output frequency equal to the carrier frequency plus. Okay. Now, let us discuss this a little bit. Right? What's going to happen? So now we connect this guy here. And what we also connect is a local oscillator. Let me increase a little bit again. So we have local oscillator. Mixture. This is, as you see here, right? This is called local oscillator. Now we're going to connect the local oscillator thing to the frequency counter. Where is frequency counter here? Yeah, there you go. Now we are already disconnect the other one, right? I'm just going to use this so that it seems like this is also connected, but for this case, this is not connected. Right, let me see. Okay. Oops. Okay, then, I just move a little bit, right? So now so I connect the local oscillator to this frequency counter so that we can see what is the frequency of the local oscillator, right? Now, this is the tuning knob, or RS tuning. So remember, on the generator side, we have a RS tuning, right? Here we have a RS tuning to tune the frequency of the carrier or change the frequency of the carrier. Now here we have another RS tuning on the receiver side, this guy. What we do with this is to change the frequency of something, right? Now that something is called local oscillator, meaning we are creating on the receiver side, we are creating another frequency, just like carrier, right? On the generator side, we create carrier frequency. On the receiver side, we create similar to carrier frequency, but it is called local oscillator, right? Now, what we need to know here, if it is a standard receiver, then there is a relation between the local oscillator and the carrier frequency of the incoming signal, right? So this is what the equation is. The local oscillator equals the carrier frequency plus another frequency. Hello? You have any question? Anyone has any question? Okay. So you are hearing me well, right?
Yes.
Yeah.
Okay, good.
Yes,
Right.
Professor.
Maybe somebody was talking to someone else. Okay, so here, what is it is local oscillator that we just saw, this local oscillator, has a relation with the carrier frequency of incoming signal with this relation, FC plus FIF. FIF is called intermediate frequency. Now we're going to discuss this more on the couple of next labs. But here what happened is local oscillator has to have this relation, a strong relation. Now for this particular device, the IF is always fixed to 455 kilohertz. This is a fixed value. This is always constant, right? For this device, for this equipment. So in that case, local oscillator equals, what was the value of FC? 1000 kilohertz, right? That's the FC. Plus IF is 455. So local oscillator equals 1455, right? Now here, what it means by 1455, what do we have to do with this? Now what it means is, if the local oscillator is equal to 1455, right? And how do you know it is equal to 1455? By using the frequency counter. The frequency counter will display here what is the frequency of the local oscillator, right? By connecting this way. Now you're tuning this to change the frequency. If it is not 1455, then you can change it to 1455. When it is 1455, then the relation holds, right? Our IF is 455 and our FC is 1000. So, and also local oscillator becomes 1455. Now the relation holds, right? Now I may ask, let me see, I may ask upon T, if the local oscillator is not 1455, what will happen? As you see here, FC is 1000 kilohertz. FIF is 455. So that to hold this relation, FLO, which is the local oscillator, has to be 1455. But if what we generate here is not equal to 1455, what is going to happen? F on T.
So what I think is going to happen is that whatever we are assigning to the intermediate frequency
Right.
that determine the value of the local oscillator because it's added
Yeah.
with
So
the carrier frequency.
right. So here, what happened is this intermediate frequency is fixed. This
Oh.
is fixed. We can't do anything. It's always 455, right? And the AM generation, from the AM generation, the carrier frequency that we put was 1000 kilohertz. So these two are already fixed. We can't do anything because we already sent the AM with this carrier frequency, and our IF is always fixed to 455. Now to hold the equation, F, like the local oscillator, has to be 1455. But if it is not 1455, what does that mean, or what may happen? That was the question. So IF is fixed to 455. You can't do anything with that, right? So do you have any guess? If it is not 1455, what may happen?
Professor, it's as if here, I think we'll hear noise.
Noise from Maybe somebody else also turned their mic, or I don't know. Is it from me?
No, I'm
So,
saying maybe we will hear noise if it's not 1455.
oh, I see. Okay, I thought we were hearing noise from this Blackboard lecture. Okay, uh, maybe, maybe not. Okay, anybody else has any guess?
This is MD Saad Ahmed. So if the local oscillator is not 40, that means the carrier frequency is less than, so that the envelope gonna be overlapped.
Hmm.
Hey, Professor, this is Gregory Dopi. So
Yes, go ahead.
I'm thinking that since this is the receiver, if the frequency is less than 455, then you'll have issues demodulating the signal, so it may be distorted. You might not get back the exact same signal that was sent when the initial AM signal was transmitted.
That's that's very close, very close. Good. So the thing is, I don't know whether you remember like old-fashioned radio, right? So when you pick a channel, what do you usually do? You uh, spin or rotate a knob, right? And then you pick one of the channel, right? And this is also true it was also true for like picking channel for television. It's old time television. There's a knob. Right now we have remote control. You just press button and then it comes. But usually we have a knob. So what it means is whenever you rotate this knob, right, RS tuning of the local oscillator, when your frequency of the local oscillator becomes 1455, you start to receive the AM signal that is coming to it. When it is like higher or lower, you are not getting this signal anymore. So what it means is you try to tune your local oscillator to the incoming signal so that you can only pick that signal, right? So when the local oscillator becomes 1455, your receiver tune to the incoming signal. Does that make sense, or do you get the point?
One question, Professor.
Yes.
This is Kaya Ponte. So the frequency for the intermediate frequency, it is always going to be 455 kilohertz, right? No matter what.
Right. No matter what. Yes.
Okay.
Yeah. So it means like whenever your local oscillator is 1455, then it holds this equation. What it means is now it can receive the incoming carrier, which is 1000 kilohertz. If it is go beyond this, both way, more or less, it's not gonna receive that 1000 kilohertz signal, right? So what it means is you are tuning. Tuning means your carrier is somewhere there, right? You are tuning, maybe you are coming from the left side, right, towards it, and then you match with this, then you're receiving the signal. Once you are getting away from it, you're all again losing the signals, right? So this is what happened. So that's what is called is when it matches, then yeah. So here it says fine tune the receiver until, meaning you change the local oscillator signal as it is connected to the frequency counter. You can see what is frequency for this time, right? So you have to fine tune a receiver until the signal is loudest. So when you change the volume of, change the local oscillator, you're gonna see the signal is coming slowly, slowly, and you can hear the signal a little bit louder and louder and louder at time. When it tuned right at that spot, you hear the signal the loudest, right? So that means now it is tuned to that particular carrier, right? So once you tune to the particular carrier, you only receive whatever is belong to the carrier, meaning whatever carrier is carrying. That is, the carrier was carrying the message signal of 2 kilohertz, right? At that point. So now, once you tune the carrier, like now you start to hear this 2 kilohertz tone, which is now is called tune into the broadcast. So whatever is broadcast, the broadcast was 2 kilohertz that we are sending. Now, when you tune your local oscillator changing, once the local oscillator gets right at 1455 kilohertz, now you tune to the incoming signal, and now you hear the tune the loudest. Right. Now you have
Professor,
matched.
I have a
Yes.
question. So, if this is Jesus Figueroa, so if the carrier
Go ahead.
were say, if the carrier were say, I don't know, 1200 kilohertz instead
Uh
of
huh. Uh huh.
1000 kilohertz, so
Right.
you would need F local to be 1655, right?
Your carrier is 1200, right?
Yes.
Yes, exactly. What
Okay.
what it means is, if you send a carrier with 1200 kilohertz, right? Now you have to tune your local oscillator to 1655 to get that signal, right? So
Got it.
you actually bring a very interesting thing is, let's say we are sending two carrier. One is 1 kilohertz and 1000 kilohertz, and the other one is 1200 kilohertz. 12, let's say, yeah, 1200 kilohertz. Now, when the local oscillator is get 1455, it will get the first carrier. So now it can hear whatever message is with the first carrier. Now, if you change the local oscillator to 1655, now it is now hearing whatever is with the second carrier, right? This is how, when you change the local oscillator, you can pick different carrier, meaning you can pick different channels, right? So you have all the channels there. You just change the local oscillator and get it tuned to a particular channel, meaning the relation has to be FC plus IF. Whenever is FC plus, whatever FC is there, if this relation holds, then that receiver tuned to that particular carrier, and now it's receiving signal from that particular carrier only. Other channels are blinded. You can't hear other channels anymore, right? So this is an interesting point, as you just mentioned, if there is a different carrier frequency available. Now with that, as you see here, determine the local oscillator for a carrier of something else, right? So for this particular carrier, what should be the local oscillator? Or what frequency do you tune the local oscillator to receive that particular carrier? So the relation is straightforward. You have 1510 plus 455, right? Very simple math, okay? Now, disconnect the frequency counter from OSC output and connect it to the terminal 6 on the AM generator module in place of AM receiver. Temporarily disconnect the audio output and turn on generator, adjust the RF frequency carrier. Okay, so now what you did is connect it to the term. So now you have picked a different frequency, right? So the carrier frequency is now 1100. It was 1000, now it is 1100. Readjust the RF gain to the 1/4, reconnect the message signal to audio input of the, okay, so again, so what happened for these three procedures is we just check the whole procedure, whole thing by using 1 kilohertz, 1000 kilohertz carrier. Now we change the carrier to 1100 kilohertz, right? And do the same thing. Again, we change everything so that now it works only for 1100 kilohertz. So then what frequency of local oscillator should be so that you now tune to this new carrier, right? So again, it's straightforward. 1100 kilohertz plus 455. That you're gonna uh, you have to make the local oscillator that value so that you can pick the new carrier, right? And here calculate this minus this, right? For step 12 and 15. Because in reality, in theory, because we are just going through the theory, in theory, we can put exact value. Let's say our local oscillator has to be 1100 kilohertz plus 455 kilohertz. So it's gonna be 1555 kilohertz. But in reality, it might be a little bit off, right? As it says at the beginning, uh, for a local oscillator to tune to this, it might not be exactly 1455. It might be a little bit off. Let's say within 1450 to 1460. On that range, if it is a real equipment, in that range, it may appear. Because in real equipment, you cannot like exactly fix the frequency. It may be a little bit different than what you think or what the frequency counter shows, right? Something like it. So in reality, it might not be exactly 1450, maybe 1457, 1453, something like it, right? So if we had the chance to do it in real, like in classroom environment, then you're probably gonna find this is not exactly 1555, and the other one is not exactly 1455. So in that case, the 16 says, okay, if you subtract this, try to find what is the intermediate frequency, right? For this particular case, in theory, we're gonna get both equal to 455 kilohertz. But in actual case, it might be, let's say, 453. Sometimes it might appear 456 or 457, something like it, right? So this is just to show in real equipment, it might be a little bit different. Not exactly as the theory says. Okay, so far this is what we have for today's lab, right? So do you have any question in general?
Professor, it's me Asif here.
Yes, go ahead.
So basically, next Monday we don't have class, right? So the following Monday we have to have a post lab to answer all these questions that you just explained to us, and a pre lab, right, for the next lab that's coming up.
Right, right, right. As just as you pointed out, good thing, just to do a review of how to do the post lab, right?
Yeah.
So here, as you see, uh, so in procedure number 1, we don't have anything, right? It's just the setup, right? Procedure number 2, uh, uh, yeah, here you can say something. So you start the first procedure that you're gonna explain or answer is procedure 2, and then just put your explanation that we discussed. Procedure 3, you can put some arbitrary value, the lowest value of this, the higher value of this, something. And then 4 has nothing, 5 has nothing, 6, yeah, 6 has something. 6 is you can use your pre-lab output to show the thing, right? For this case. And you can vary some of the pre-lab output here, like we vary here carrier level and RF gain. So the difference between RF gain and carrier level is on your pre-lab, you can put a what we call gain block, right? On a Simulink, you have a gain block. You can just put a gain block right after you have done the modulation, right? And then you can put a value of higher than 1, lower than 1, and see what happens. Now also, you can change the amplitude of the carrier level only, and then you see the output, right? So this way you can vary your pre-lab thing, and then you can nicely get the output required to answer this question, right? That will be not that difficult. And then we discuss about this, what happened. So 7 is gonna be there, 8 has answer, I think 9 has answer, 10 has answer, 11, I don't think so, 12, yeah, 12 has answer here. Then 13, 14 has none, 15 has, and 16 has. Yeah, so not all of them has anything to do with your lab, right? Some of them. And also, when you use the carrier change of carrier level and the gain, try to use your pre-lab module, like Simulink module, put an extra gain at the end of the modulation and then increase the value beyond 1 and less than 1 and to see what happened, and also change the amplitude of the carrier, only the carrier, and see what happened. And you can put those, let's say, the figure or waveform that you see, and you can put onto your lab report, right?
And Professor, at the end of 16, they're asking for the explain the results. So are we explaining the entire experiment or just the results?
No,
of
only
16?
only 16, only 16.
Okay.
Why you get, you can just say in theory you're always gonna get 455, but in reality it might not be exactly 455. You might get like 453, 454, or 456, 457, something like that, right? So any more questions?
I have a question, Professor. This is Gregory Delbury. Are you going to send us a
Yes, go
description
ahead.
for the pre-lab for the second lab?
Yes, of course. Yeah, just
Okay.
like the lab 1, I'm gonna describe, and I'm also gonna put this thing, the connection that we did today, right? I'm gonna send this figure as well, if it might help you to explain things, right? Just
Mhm.
this part, right? So you can remember what we did, and then you can explain. It will be better for you to explain. Yep.
Thank you.
And hello,
You're
Professor.
welcome. Yes.
So for this lab, we have 2 weeks, right? Since next Monday we don't have class.
Right. Exactly. Right.
Okay.
It's the following week, not this coming week.
Also the
And
P-Lab. Yes.
Go ahead.
Yeah, I was going to say the P-Lab also due on is going to be on following week, right?
Say that again.
The pre-lab.
Pre-lab. Yeah. So I'm gonna again get a pre-lab link. Let's say pre-lab 2, and maybe some questions or something, some instruction what you have to do, right? Just like pre-lab 1, right? Just follow that one and then put output. You don't have to like follow all the instructions that is in the procedure of lab 2. Right.
and Professor, um, um, can you grade our pre-lab so that we know that our circuit was correct, or I mean, we got something reasonable?
Yeah, I'm gonna grade like pre-lab, post-lab after this one, because I gave you the chance even to submit it in the last minute before the lab starts.
Okay.
So once the lab is done, then I'm gonna start evaluating your pre-lab. Yes.
And just a quick question about the grading, Professor. In the syllabus, it said that if you make a mistake, it's gonna be a negative marking. So, I mean, if you don't answer and make a mistake about that one.
Yeah, the mistake is, what I mean by this is not the wrong answer. By mistake, you did not answer any questions.
Okay, get you.
Okay, so in
Thank you,
that
Professor.
case, you're gonna get negative. But if your answer is wrong, you're not gonna get any negative. It just you're not gonna get that point for that particular answer.
Okay, Professor. Thank you.
You're welcome. Anyone else?